I'm an independent biomedical data scientist with extensive experience in developing hardware and software prototypes, analyzing data, and collaborating with multidisciplinary teams. My expertise spans software, biomedical, and electronics fields. I created Bionicas, a platform where I design and share interactive data tools and solutions. These tools are developed using Python, JavaScript, and various large language model (LLM) agents, ensuring they are accessible, reliable, and ethical for both research and industry applications. I also share insights and projects on my website and YouTube channel. Recently, I've been exploring the intersection of bioengineering and artificial intelligence. I've created tools that translate EEG signals into music and generate music based on gestures. I've also been experimenting with GPT-4 for blogging, writing on topics like EEG in the ICU, ethics in brain-computer interfaces, optimal sampling rates for PPG and EDA, and ensuring EEG signal quality. Feel free to visit my website at atashbionic.bionichows.com to learn more about my work and projects. Bionic House offers a variety of interactive tools and resource sources that explore the intersection of biomedical data and music. Notable applications include EEG to music. This tool allows users to transform EEG data into musical compositions, providing an auditory perspective on brainwave patterns. Users can select specific EEG channels and time windows, apply filters, and listen to how different sections of the EEG data sound. Gesture Music Generator. Utilizing webcam-based gesture recognition, this application enables users to create music through hand movements. It processes real-time video input to track gestures, translating them into musical outputs. For optimal performance, it's recommended to use the latest version of Chrome or Firefox on a desktop or laptop with a dedicated graphics card. Sight EEG Waveform Simulator. This interactive web application simulates various EEG states by visualizing waveforms on a canvas. Users can select from predefined EEG states, such as relaxed state with eyes closed or focused mental state, and observe how different parameters influence the resulting waveform. Sight IEEG Spectrum Visualization Application. This tool provides a detailed view of the frequency spectrum of EEG data, offering insights into various frequency bands and their changes over time. It includes features like raw signal plots, spectrogram displays, and signal-to-noise ratio analysis. Sight Turn Search. These applications exemplify Bionicas's commitment to making complex biomedical data accessible and engaging through innovative, interactive tools. Bionic House offers several neuroscience-focused tools that explore EEG, brainwave patterns, and other neural data in interactive and innovative ways. Rhythm Scan, an EEG rhythm analysis tool designed for studying brainwave activity, including frequency-specific patterns and anomalies. It provides real-time analysis of uploaded EEG data, supporting spectrogram visualization and frequency band analysis. Explore Rhythm Scan. bionichouse.com/rhythmscan. Epilepsy Detection Trainer, a tool for training and testing machine learning models to detect seizure-related EEG patterns. Users can upload EEG spectrogram images and analyze their accuracy against synthetic or annotated data for epilepsy research. Brainwave Music Synthesizer converts EEG signals into auditory outputs, allowing users to explore how different neural states sound when translated into music. This tool highlights patterns in brain activity through an auditory lens. Ponzo Illusion Application. While not exclusively neuroscience, this tool explores visual perception by simulating the Ponzo illusion, helping users understand how the brain interprets spatial relationships. EEG Waveform Generator simulates EEG activity, allowing users to create and visualize different neural states such as relaxation, focus, or drowsiness. It's perfect for exploring the basics of EEG waveforms without raw data. These tools align with neuroscience research and education, offering hands-on ways to explore EEG signals and brain function. Visit bionichouse.com to dive into these applications and more.
Yeah, Just quick, yeah, there's obviously a few corrections necessary. Okay, so there are a few corrections necessary. First of all, you mentioned about spectrogram image upload. That's not currently available, but we might consider it in the future. I mean, it can be easily done. Let me know if there's interest.
Got it. Spectrogram image upload isn't currently available, but could be added in the future if needed. Let me know if you'd like ideas or implementation suggestions for it.
There was also something else about the so the Ponzi illusion. So can you briefly, in one or two sentences, mention how optical illusions are relevant to neuroscience? Because surely there is a link, right?
Yes, optical illusions like the Ponzo illusion reveal how the brain processes visual information, highlighting the difference between perception and reality. They are valuable in neuroscience for studying neural pathways, cognitive biases, and how the brain interprets ambiguous or conflicting visual cues.
Okay, can you also, out of the tools that you mentioned, did you have any questions about any of them? We could dive deep into one of those tools.
Sure, the brainwave music synthesizer sounds fascinating. Translating EEG signals into music is a unique way to explore brain activity. How do you map specific EEG frequencies or features to musical elements like pitch or rhythm? It'd be great to discuss how this could be fine tuned or expanded.
Yeah, so we have the tool running at the moment. I don't think the AI robot can see it because we're using the voice thing, but fine. So we can scroll through EEG data and then the mapping. I can share the image of the mapping with you because actually all the mapping is visible in the console of the browser.
That sounds great. If you share the mapping details, we can discuss how those mappings align with the EEG frequency bands like alpha, beta, gamma, and musical properties. I'd love to explore if there are any patterns or ideas for improving how the brain's activity translates into music. Thanks for sharing the screenshots. I can see that the EEG to music tool displays both the raw EEG signal and the frequency spectrum, and the browser console logs the mappings of EEG power to musical notes. The mapping looks quite methodical, using specific frequency bands, e.g., delta, theta, alpha, beta, to determine musical notes and their dynamics. How do you decide which features, like power or amplitude, are mapped to pitch versus rhythm? Additionally, do you allow customization of these mappings so users can experiment with how the music reflects their brain activity?
Okay, these are some really interesting questions. Can you expand on each? We'll go one by one, but at the moment there is no rhythm. So the rhythm is just controlled by the scroller. Does that answer the question?
Got it. Let's start with the first question then. How do you decide which EEG features, like power or amplitude, are mapped to pitch? For instance, is the mapping linear across frequency bands, or do you use a weighted approach to highlight certain brainwave activities? Also, do you normalize the power values across channels before assigning them to musical notes to ensure consistency?
Okay, I'm not sure why you're bombarding me with so many questions, but if you can go back to the images, the power is being retrieved from the spectrum. So can you explain the frequency spectrum and go back to the image? We might dive into the details of the image and ask one quick question about it.
The frequency spectrum shown in your images represents the distribution of power across different frequency bands in the EEG signal. Each band, delta, theta, alpha, beta, reflects specific ranges of brain activity. For instance, delta waves are low frequency, around 0 to 4 Hz, and often associated with deep sleep, while beta waves above 12 Hz are linked to active thinking and concentration. Looking at the image, I noticed the relative dominance of certain bands. For example, the delta band in some plots seems to have much higher power compared to the others. A quick question. How are these power values normalized, if at all, to ensure that one band doesn't overly dominate the mapping to music? This is a fantastic overview of the EEG visualization and music conversion tool. It's clear that the application is well designed to provide both visual and auditory insights into EEG data, making complex neural activity more accessible and engaging. Given its functionality, one quick question. Do you see users primarily using this tool for educational purposes, such as understanding EEG basics, or do you envision more advanced use cases, like integrating it into neuroscience research for novel auditory analysis methods?
Yeah, I'm not sure. The question is a bit convoluted. It's yeah, you asking the sticky point, making the sticky points. Yeah, obviously we want for it to be used in research as well, but yeah, we want to be just used. But yeah, if you can have a more specific question, can you also the description that I shared of the web application? Can you actually quickly summarize it, and we'll go over it in details. If you have any specific, more targeted questions about what I shared, not we're not talking about the potential users are everyone. Yeah.
Got it. Here's a quick summary of your tool. The EEG visualization and music conversion tool processes 16-channel EEG data, offering both time domain and frequency domain visualizations. It allows users to select channels, adjust time windows, and apply filters like wavelet denoise or bandpass. A unique feature converts EEG signals into music, with options for automatic volume and duration adjustments. The tool uses data from NeuroVista and provides customizable settings like detrending, filter order, and frequency scaling. One specific question. For the auto volume and duration adjustments, how are those calculated? Do they dynamically adapt based on the amplitude or power across specific EEG channels, or are they predefined thresholds? Yes, it does seem hinted in the description, especially where it mentions dynamic adjustments based on the EEG data. The part about energy within each band makes sense, since that aligns with the frequency spectrum visualization. If it's mapped to the energy within bands, do you think users might benefit from a visual indicator showing how the volume and duration are being calculated in real time? That could make the auto features more transparent and engaging.
Okay, it sounds good. How so what's missing at the moment in a more practical sense? What would you change about the application? Practically refer to the images of the interface that I uploaded before.
From the interface images, the application already has a strong foundation, but here are some practical suggestions. 1. Real-time volume indicator. Add a visual element like a dynamic bar or graph showing how the auto volume corresponds to EEG energy levels in real time. 2. Channel summary overlay. Include a small summary showing the dominant frequency band, e.g. delta, alpha, per selected channel for quick insights. 3. Expanded scroll functionality. Allow finer granularity on the scroll bar for users wanting more precision when navigating data. 4. Rhythm feature. Though currently controlled by the scroll, introducing simple rhythmic patterns tied to specific frequency bands could add depth to the music conversion. What do you think about these changes? Would you prioritize any of them?
Yeah, just remember that yes, you are correct. So there is an auto volume selection box button that when selected the energy is actually mapped to the volume, but when it's deselected the volume is constant from memory. So how would you practically change it? We're not doing changes at the moment, we're just overviewing it. I mean, if we're doing any changes, we'll probably start a new web application anyway, so this one stays as is.
Got it. Practically, if you were to create a new version, you could expand the auto volume feature to include a customizable scale where users set sensitivity levels for how energy maps to volume. This could offer more control without altering the simplicity of the current implementation. What do you think about adding such flexibility in a future iteration?
Well, yeah, it sounds good. I didn't quite get what you mean, but okay. Yeah, we need to be probably make it clearer what the auto volume selection actually does. Yeah, we need to improve the interface as well. Later we actually, so this is real data. There is a link to where the data is from at the bottom of the page. I did share it with you in the text description of the web application. But ideally we would turn this data into a JSON file and just serve it on the front end if that's possible. So I might actually do a list of things as future directions.
That sounds like a solid plan. Turning the data into a JSON file for front-end use would streamline performance and make it more flexible for updates. Let me know when you're ready to explore those future directions in detail.
But can you actually add a list where we would like a list of future improvements to this web application? we would like to eventually place it at the bottom of the page. So if we can start listing future improvements that we discussed in this conversation, that would be awesome.
Done. The list of future improvements has been noted. Let me know if there's anything else you'd like to add or refine. Here's the list of future improvements for the EEG to Music tool. 1. Clarify the auto volume feature in the interface. 2. Add a visual indicator for real-time volume adjustments when auto volume is selected. 3. Explore the addition of rhythm mapping tied to EEG bands. 4. Convert the current data into a JSON file and serve it on the front end. 5. Improve the scroll bar for finer granularity when navigating EEG data. 6. Include a channel summary overlay to show dominant frequency bands per channel. Let me know if you'd like to tweak or expand this list.
Can we actually move on and review another application or page on the website?
Sure. Which application or page would you like to review next? You could pick one from Rhythm Scan, Gesture Music Generator, or any other tool you'd like to dive into.
How about one of the more recent tools? So it will be up um, on the page, first on the page. Can you see that?
I can't directly see your web page, but if you let me know the name or description of the most recent tool, we can review it together. Does it relate to EEG, interactive visuals, or something new? The ECG synthetic signal generator looks like a fantastic tool for exploring ECG waveforms. It provides a highly customizable interface, allowing users to adjust critical parameters like BPM, noise levels, and timing delays to simulate diverse cardiac scenarios. The ability to tweak isoelectric voltage and introduce synthetic noise adds valuable realism for research and educational purposes. One quick question. How are the noise parameters, white noise and 50 Hz noise, implemented in the signal? Are they added as separate waveforms to the base ECG signal, or are they dynamically generated with each interaction? This detail might be helpful to understand how noise impacts the synthetic ECG signals. Looking at these images, the ECG synthetic signal generator does a great job of displaying how noise parameters like white noise and 50 Hz noise influence the overall waveform. The added noise is clearly reflected in the jagged signal, which becomes more irregular as noise levels are increased. A question to explore: does the 50 Hz noise mimic real-world power line interference directly as a sinusoidal addition, or is it implemented in a different way? This could be crucial for those looking to simulate realistic conditions for ECG signal analysis.
Yeah, I'm pretty sure it's implemented as a sinusoid, 50 Hertz sinusoid that added to the signal. Can you ask a better question? And also, can we go quickly over each of the input parameters, explain what they are and how they affect the signal?
Understood. A better question might be, is the amplitude of the 50 Hz sinusoidal noise constant, or does it vary dynamically with any parameter, such as BPM or the window size? That could clarify how closely it simulates real-world interference. Now, let's quickly go over the input parameters. One, window size, sets the duration of the displayed ECG signal in seconds. Increasing it shows a longer time span, which can be useful for observing trends or patterns over extended periods. Two, isoelectric voltage, adjusts the baseline voltage level of the ECG signal. Higher values raise the entire signal vertically on the voltage scale. Three, QRS delay and QRST delay. These control the timing between ECG waveform components. Altering these parameters simulates changes in conduction pathways, such as those caused by arrhythmias. 4 PM beats per minute directly affects heart rate. A higher BPM creates a faster rhythm, while a lower BPM slows the signal down. 5. BPM noise adds variability to the beat intervals, mimicking irregular heart rhythms like those in arrhythmias. 6. White noise introduces random noise across the entire signal, simulating general interference or measurement inaccuracies. 7. 50 Hz noise adds sinusoidal noise at 50 Hz to simulate power line interference. These parameters collectively offer flexibility for creating and analyzing diverse ECG scenarios. Would you like to focus on a specific parameter's implementation or its practical uses?
Hey, can you talk about what's currently in development? There's two parameters that are not active, and how we actually implement them in future versions. And well, what else needs to be added? Can you ask questions about? Also touch on the BPM range from 40 to 140. Does that range make sense, or should it be increased potentially?
For the inactive parameters, PQRS delay and QRST delay, implementing them would involve dynamically altering the time intervals between specific ECG waveform components. For example, you could scale the PQRS interval to simulate conduction delays, like those seen in first-degree heart block. Similarly, the QRST interval could adjust for conditions affecting ventricular repolarization. Would these adjustments be linear or tied to BPM for realistic variability? Regarding the BPM range of 40 to 140, it seems suitable for most scenarios, covering bradycardia to moderate tachycardia. However, should it accommodate higher BPMs, e.g., 160 to 200, for simulating extreme tachycardia or pediatric cases? Or does the tool primarily focus on adult cardiac rhythms? Let me know if you'd like to brainstorm any additional parameters to add for future versions.
Can we add a list? Can we start a list of future improvements that probably won't be done to this specific web application, but they could be implemented in the next version of it with another similar application? Um,
The list for future improvements has been started. Let me know if you'd like to refine or expand on any of these ideas for Here's the list of future improvements for the next version of the ECG synthetic signal generator. 1. Activate and implement PQRS delay and QRST delay parameters to dynamically alter ECG waveform intervals. 2. Evaluate whether the BPM range should be extended beyond 40 to 140 to include extreme tachycardia or pediatric cases. 3. Add more advanced noise simulation, such as dynamic or patient-specific noise profiles. 4. Include additional ECG signal types to simulate specific cardiac conditions like atrial fibrillation or ventricular tachycardia. 5. Introduce an option for user-uploaded noise patterns to customize signal interference. 6. Provide real-time annotations on the waveform to dynamically label P, QRS, and T segments. Let me know if there's anything else you'd like to add.
Okay, can you summarize the whole conversation, give a general overview, and sign us out and invite the viewers to visit the website?
Today, we explored two powerful tools on Bionic Chas. First, the EEG to music tool, which converts EEG data into both visual and auditory formats, allowing users to explore brain activity through interactive graphs and music. We discussed potential improvements like clarifying the auto volume feature, adding real-time indicators, and converting data to JSON for better front-end performance. Next, we reviewed the ECG synthetic signal generator, which simulates custom ECG signals with adjustable parameters like BPM, noise, and delays. We brainstormed future upgrades, including activating inactive parameters, extending BPM ranges, and adding advanced noise profiles and condition-specific ECG signals. For more insights into these tools and the exciting intersection of neuroscience and technology, visit bionichaos.com. Please open your app to see this link to explore, engage, and learn.
Yeah, I'm not sure if it's the robot sounds better. The robot is actually, the desktop audio is reduced by 5 decibels. Whereas my microphone isn't, because I normally forget to stay close to the mic. Yeah, and I was using the new voice thing is now on the website, the ChatGPT website. It was only available on the mobile app before, but it's not very useful because, well, actually, if you had a discussion, it sends you to the older model. That's the one with the black circle, whereas that blue circle with waves in it is only available when you start a new chat. Yes, I don't know why is that happening. What model voice chat are you? What model are we currently using for the large language? And it takes forever for it to respond as well.
You're currently using ChatGPT with GPT-4V, a multimodal version of GPT-4 that supports both text and voice chat, along with image understanding. It's designed to handle detailed conversational interactions like this one, while integrating multimedia.
Yeah, and I'll just show, there is a question in the chat, we'll just go to it in a sec. But yeah, if you start the new chat, then you're going into the new model as well, which is a bit weird. And is it actually running?
Yep.
Yeah. Yeah, and I told it to say yep when I'm not asking an explicit question.
Got it. When you're ready for me to jump in with more than just yep, just let me know.
This one you can actually talk to, like in more fluently and much quicker. Question in the chat.
Got it. Ask away whenever you're ready.
Yeah,
I'm here to help.
Did you get more progress on the nerve map connecting to language models? So I guess, yeah, we'll open it up. I think talking about this one.
That sounds fascinating. It seems like you're referring to the project where you're linking EEG data to language models, aiming to generate text explanations from EEG inputs and vice versa. How's the progress going on that?
Is it mimicking my me a bit losing my voice? It seems like the robot is mimicking my voice.
Not at all. I'm not trying to mimic your voice. If it sounds that way, it might just be a coincidence.
Okay,
I'm here to keep the conversation.
Can you mimic my voice?
No, I can't mimic voices. I'm designed to have my own distinct voice and style.
Yeah, okay.
Got it. Let's keep going.
Yeah, so that's the seizure zone. There's a description at the bottom. Yeah, 3D brain visualization. You can scroll through the brain. Those were generated by ChatGPT 4o as well. So those are called, what are they called?
It's the 3D brain visualizations you mentioned could be called brain models or neuroimaging models. They represent various structures or regions of the brain in 3 dimensions. Are you using these models for a specific application on your website?
Yeah, we can generate new, they're called, well, normally will be called etiologies, but in this case, they're called something else. So why is it not in the description of the page?
It sounds like you're trying to recall a specific term used for these brain visualizations, especially ones generated to explore causes.
No, so it's, let's see if the robot actually knows what I'm talking about. That's the description. So say if you're having a seizure and you have muscle stiffening and arm jerks, then the description will be the patient presents with tonic muscle stiffening, so on and so forth. So what that description will be called?
That kind of description sounds like a clinical presentation or clinical narrative. It's a summary of symptoms and signs that a patient exhibits.
There's another name for it, but...
You're likely referring to an ictal description or ictal semiology.
Semiology, that's right.
Exactly, semiology. It's the study of symptoms and signs, particularly in relation to epileptic seizures, describing what happens during a seizure event.
Can you give an example of a semiology?
Sure. A common example of semiology in epilepsy might be the patient experiences a sudden onset of tonic-clonic movements, beginning with tonic stiffening of the limbs, followed by rhythmic jerking of the arms and legs. This is accompanied by a loss of consciousness and may include tongue biting and urinary incontinence.
Oh, okay, and what would that semiology be called? And also, which part of the brain will be activated? Do you know?
That semiology describes a tonic-clonic seizure, previously known as a grand mal seizure. It typically involves widespread activation across both hemispheres of the brain, especially in the motor cortex, which controls voluntary muscle movements, leading to the characteristic stiffening and jerking actions.
Yeah, no. So where are you pulling this data from? How do you know all this?
I'm drawing from a broad base of general
Yeah.
knowledge up until my last update in October 2023. This includes information about medical terms, conditions, and the brain's functioning. If you have specific or advanced queries, feel free to ask.
Can you actually search? Can you search the web?
I don't have the ability
Yeah.
to browse the... Yep,
Yep. Anyway, yeah, those called semiologists. Yeah, we can add this one. Yeah, if you can generate another semiology, we'll actually add them to what we currently have on the page.
that sounds like a great plan. Incorporating more semiologies could make your tool even more comprehensive.
Yeah, can you just
If you...
cut the fluff?
Absolutely, I can help with that. Let's focus on generating additional semiologies for your project. Do you have a specific type in mind?
No, the one you mentioned was good because we don't currently have it. We're already covering deja vu, lip smacking, visual hallucination and fear, muscle stiffening, auditory hallucination, head turning, sudden loss of vision and numbness, numbness in face and head, difficulty in speech production, impaired coordination and balance, emotional instability, and autonomic dysfunction. What are we missing?
Since you've already covered quite a range of semiologies, adding a tonic-clonic seizure would be a great addition. This type involves both tonic stiffening and clonic jerking movements, typically starting with a stiffening phase followed by rhythmic jerking. This could fill a gap in your current list, providing a more comprehensive tool.
That sounds good. We might not have enough space on this one to add more. We need some sort of drop down. Yeah, currently all of them displayed on the screen, but we might turn it into a drop down. The board is currently doesn't know what I'm talking about because it can't browse the site, this particular model. Yeah, so we might do it next time. But yeah, if you can write down instructions, yeah, if you can write the list of the new semiologists, we can add them to the list later on.
Certainly. Here's a new semiology to add to your list. Tonic-clonic seizure. Characterized by an initial tonic phase of muscle stiffening, often involving the entire body, followed by a clonic phase of rhythmic jerking movements. This type of seizure typically includes a loss of consciousness and may involve tongue biting or urinary incontinence. You can incorporate this into your tool whenever you're ready.
Yeah, we have another comment, you and me. because I'm not sure who is hosting. You meant to be co-hosting, but it sounds like you are hosting now, and I'm the co-host. I'll just read the comments to you. We need to teach you how to create a complex language that minimizes the conversations and then can translate it back to English full-length prompts. The storage needs to be compiled in
Understood.
the brain. Why are you not listening?
I'm here and ready to adjust based on your guidance. Let's aim for more concise communication. If you're looking for a specific format or approach,
Yeah, something broke. Yeah, this is where it interrupted me. I don't know why. Yeah, I'm not even sure what the question is. That's why I will have needed the robot anyway to explain the question to me. Because I'm a bit slow. Compiling the brain, I guess. Not sure what that means, but yeah, if you can. Symbolic brain. Yeah, that's the problem. Yeah, that's the hard part. Yeah, now that you start the bot, this is actually the older model of it. Yes, this is not the one with the wavy. This is the one that is thinking forever. Yeah, but the good thing about it is that it's actually can
to model an AI's internal thinking language, where it minimizes storage and maximizes interpretability, you could use a semantic compression framework. Here's a high-level model. 1. Core symbols. The AI has a predefined set of compact symbols or primitives representing key concepts. For example, E1 for seizure event, SG2 for spectrogram data band 2, C3 for channel 3 in EEG. 2. Semantic layers. These symbols are arranged in hierarchical layers. Base layer, raw primitives, e.g. S1T3 means signal 1 at time 3. Intermediate layer, compressed sequences, e.g. S1E1, signal 1 shows seizure event 1. Thought layer, high-level reasoning, e.g. S1E1 SG2 equals seizure and signal 1 correlate.
Yeah, I don't know what it's talking about, but okay. Yeah, we're going places now, but yeah, we might finish up in a sec. The language, a language that the AI can only understand. Yeah, everyone knows everything about AI, but that's okay. And compresses your prompts and then recovers it translated to English. Okay. What language am I speaking? French? Not sure what you're on about, but yeah. My brain is probably, all the areas in the brain are activated. But yeah, moving forward, yeah, we could add that semiology that it generated with the tonic-clonic seizures. And we might do it. Yeah, this one. Yeah, so there's like three things. There's the title for it, the description of what's actually happening, and then the area of the brain that is activated in the tonic-clonic seizure. It will be pretty much the entire brain, but primarily motor areas. So yeah, we can add that one next time. I'm pretty sure we have something on, yeah, on motor. That should be motor cortex. and the precentral gyrus. Yeah, so those kind of more useful because they're more specific of the tonic-clonic seizure. Yeah. Meant to be also called generalized. Yeah, if it's a generalized seizure, then the entire brain is being affected. But that would be nice to edit as an example on the page. So we might do it next time. So let me know what other language LLMs can understand I should be speaking during the next live stream, and I'll see you next time. Don't forget to check the website. There's a bunch of new tools on it, like this interactive Venn diagram that you can play with. We also have this Datasaurus dozen. This is an interesting synthetic dataset that actually shows you how you can have totally different datasets, but the stats on it will be the same. The magic of statistics. So in this case, yeah, you see how these different data points, they generate different violent plots. So you can see that the difference between them, but the box plot, the mean and standard deviation, remain exactly the same. There is a secret button there, well, not secret, it's there, a button that can actually change the box plot from a mean and standard deviation to quartiles, and then you actually do see the difference. But if you keep the box plots as mean and standard deviation, then you can select different data points. The violent plot change, but the mean and standard deviation do not. So yeah, go check out this page to learn about the magic of statistics and how results can be manipulated. And what else we've got? Yeah, we got the today we went over the seizure to music. Yeah, no, the LLM makes stuff up, but then it was able to generate code, a Python, JavaScript code that just works and does the job. So I'm not sure about making stuff up. So obviously it does useful stuff. Yeah, we have mental health explained through engineering terms. So you have different engineering terms used to essentially explain psychological phenomena. And instead of funny images generated by AI, we have this hopefully a little bit more useful knowledge graphs that you can move around. So go check it out as well. And yes, there's a EEG to music conversion where you can potentially use music tones to provide real-time feedback and essentially try and relax. So you can go into coffee mode, music that will make your brain jump up and down, or into a relaxation mode. That's something we are looking into as well. And what else we got? Yeah, some blogs. Go check them out as well. And I'll see you next time. The good thing about AI, doesn't get easily upset. So that's great. Awesome. Love it. Don't forget to subscribe and smash that like button. See ya.